So for number 19, we've got a roller coaster ride involving coasting down an incline and entering a loop that's 8 meters in diameter. Now be careful on that one. For safety considerations, the roller coaster speed at the top of the loop must be such that the force of the seat on a rider is equal to the rider's weight. From what height above the bottom of the loop must the coaster descend to satisfy this requirement? So, if you think about the forces, we've got the force of gravity acting on the rider, and we want the normal force also to be the same acting on the rider downward. So, what does that mean? Well, the force of gravity is going to be the mass of the rider times gravity. The normal force, we want to be equal to that, so also that. So, the net force is going to be 2 mg. Please remember that's also equal to, or by definition, the centripetal force. Why do we need this? Well, we need to figure out velocity. How fast do they need to be moving at the top so that this occurs? Well, to do that, we need to find the centripetal acceleration first. So if you remember, mass times centripetal acceleration is equal to the centripetal force. In this case, the mass cancels here and here. And so you very quickly discover, centripetal acceleration is equal to 2g, or about 19.6 meters per second squared if we use 9.8. Using v squared over r, we can very quickly solve this. So v is going to be equal to the square root of 2gr, or plugging in our numbers. Whoops, I got this in the wrong order. My apologies. I'll have to fix that later. You'll end up with a velocity of approximately, if you plug in 9.81 and everything else, you should end up with a velocity here of about, give or take a little bit, of about 8.86 meters per second. Now I'm going to use that to figure out, all right, how high above the bottom of the loop do I need to be? So imagine there's a hill leading up to this one. What kind of energy do the cars have at the top? Well, they've got kinetic energy, but they also have gravitational potential energy because they're above the ground. And so when we solve this, at the top of the hill, we'll assume they're basically not moving. They're going to go down the hill. We'll assume no friction, so the work is going to be 0. And at the bottom, they've got some gravitational potential because they're at the top of the loop, and they have kinetic energy. And we know the velocity we want. Interestingly enough, there's the answer I was looking for, a slight order change. We can actually remove mass from all three terms. All three terms have m, dividing both sides by m, we get that. And now plugging in our numbers. The height, since the diameter of this thing was 8 meters, the height is going to be 8 meters above the ground. We're setting h equals 0 right here. And the velocity is 8.86 from right up above. And I'm going to use 9.81 for gravity. You could use 10. We can figure out the height. If you do that, you'll discover that the hill needs to be 12 meters above the bottom of the loop. So this height right here, 12 meters. If you do that, even when it gets to the top of the loop, it's going to be going at this speed, and you can solve it. Hopefully that'll help. Good luck.